We're looking at exercise 8.2, question 9, homework problems. Okay. The first question is to sketch this function. Now we've got the function, there are three separate functions here that we need to sketch. The first function is for values of x that are greater than 3. So, notice I've got different scales on the x and the y axes. It's okay to have that, to have different scales on the x and the y axis. So for the first function, I'm looking at this function up here, and I'm just going to do a quick table of values in my head. So the line that we're trying to sketch is basically y equals 2x for values of x greater than 3. Now, I am still going to do when x equals 3, but you'd put a circle around it, or we'll just put a little point, but we won't really. So when x is 3, what do you get? Right, so I'm just going to put a little point there. What about when x is 4? You get 8, and when x is 5, you get 10. So that bit for x greater than 3, now notice I haven't put it exactly where x equals 3, I've just left this bit open. Like I haven't put a circle there yet, but I've just started it a little bit greater than 3. Then, so that's the y equals 2x bit, this bit up here. That line is the y equals 2x bit for values of x greater than 3. Now the next bit we're going to do is this bit, and it's just really y equals x. Remember, function of x is y, so y equals 3, sorry. Oh, so we've got a bit of a, so what I'm going to do, I'm going to put a circle there then. Yep, and then from x equals 3, this is exactly x equals 3, so I need a dot. So from 3 to negative 2, for x values of 3 to negative 2, and that includes both points, I've got the line y equals 3. Got that? So can you see why this has to have an open circle? I didn't do it before because I wasn't sure if the next line was going to join on at that same point. But the line does not join here, so we need an open circle here, meaning that this first function up here does not include the value x equals 3. It's only for x greater than 3. This here is the line y equals 3 for the values of x being from negative 2 to positive 3. And the last function is 1 minus x squared, and it's for values of x less than negative 2. But let's still just do negative 2 as well. All right, so I'm doing this third function now. Or you can do a few other points first. Why don't you do negative 4 first? What do you get? 1 minus negative 4 squared is what? 1 minus 16 is negative 15 down here somewhere. What about when x is negative 3? You get 1 minus 9, which is negative 8, down here somewhere. What about when x is negative 2? You get 1 minus 4, but we don't include that point. So 1 minus 4, sorry girls, I've made a mistake here. That's negative 2, negative 4, negative 6. We got negative 9 for x is negative 3, about there. For x is negative 2, we got, what do we get? Negative 3, about, this is looking a real weird. All right, yeah, we got here, negative 3. So put a circle there, and it goes like this. So, all right. So when x is negative 2, we get negative 3, don't we? Which is down here. But you need an open circle because it does not include negative 2. When x is negative 3, we get negative 9, which is about down there. Girls, this is a concave down parabola. Negative x squared plus 1. So if I continued it, it would cut through up here. But it doesn't continue. It just starts from there.
Morning, Miss. Sorry for the interruption.
Or the curve is not differentiable where there are breaks in the curve, or wherever there are sharp bend, like sharp corners. So it's not differentiable at x equals negative 2 and x equals 3. Okay? Curve is not differentiable. Or you just write you cannot differentiate the curve at x equals negative 2 and x equals 3. All right, and I've just put each function there. I should really write function of x equals, function of x equals, function of x equals. But now you know that y and function of x are interchangeable. Okay? Reason it's called a function of x is because this is a function with x's in it. This one isn't, But later, if we were to do something like integrate it, which is the opposite of differentiating, it'd end up with an x in it if we had to. And this has got x's in it, okay? I'm looking at question 13. It's a trig function, and you're used to doing things like cos theta. You know how to sketch cos theta, but this is actually a year 12 function that we learn when we do the topic trig functions. So you don't have to know how to do it yet, but I'm going to choose some nice values of theta. If I put theta is 45, aren't I just working out cos 90? So I'm going to choose theta is 0. Normally we look at 0, 90, 180, 270, 360 to draw the cos curve or the sine curve. But because it's 2 theta, if I choose theta as 45, that would be a good value to choose because it gives me cos 90. Does that make sense? And I'm going to choose 90 as well. That'll give me cos 180. And I'm going to choose the equivalent of 270 would be 135. And I'm going to choose 180 will give me the normal 360 value, and that'll do, okay? This is still going to be the same shape as a cos curve, but we've got a problem here. We're multiplying it by -3. So what you can do, you can just get your calculator out if you want to, and you go -3 times cos of 0. Now, cos of 0 is what? What's cos 0? I'm going to draw a quick curve here. This is the normal cos curve down here. Cos of 0 is 1. So cos of 0, 1 times -3 is -3. Right, if theta is 245, I get cos 90. What's cos 90? 0. So times -3 is 0. If I've got cos of 2 times 90, that's the same as cos 180, which is -1. -1 times -3 is +3. Cos of 2 times 135 is 270. So cos of 270 is 0. So that'll be 0. -3 times 0. And cos of 180, sorry, cos of 2 times 180 is 360. Cos of 360 is 1. So we get -3. So now we sketch it. Girls, it's just the cos curve, but it's got, you know how it normally goes from 1 to -1? This is still the cos curve, but it's going from -3 to 3. And so when x is 0, so I'm just going to put these values here, 45. I'm not going to do it all. Did they say which values they wanted it from? It would just continue anyway once I do the curve. It would just go, you know, the cos curve and the sine curve are waves, and they just continue on and on and on. So when theta, see this is not the y and the x-axis, this is theta here, and this is function of theta. Okay? Yeah. So normally if you look at this would be y and x. If you're looking at the function of theta is in place of the y, and the theta is in place of where x would normally be. So you call this function of theta, theta, in place of normally where x, y and x would be. So when theta is 0, function of theta is -3. When theta is 45, you get 0. When theta is 90, we get 3. When it's 135, we get 0. And when it's 180, we get -3. So it's just going to be like this. Yeah. And if you were to continue it, it would just go like, okay, and it should be a bit more rounded than that. Like it goes like that. You know how they go like that? A bit more rounded. Okay? So, girls, I can't see any points of discontinuity. Did they want it from in a certain range or for a certain domain, sorry? Yeah, so it's fully differentiable because this would continue, and here, this continues back like that. It's just the cos curve with a different, what we call amplitude, and it's been flipped upside down as well because it's got the negative in front of it. But we learn that in year 12 when we do trig functions, okay? All right, is that it for exercise 8.2? Well, it means that, what's the question? This is differentiable, therefore you can differentiate this for all points. So the question was, is it differentiable? You were just looking for gaps and sharp corners. There are no gaps or sharp corners. So therefore it's differentiable for all values of theta. So therefore it's differentiable for all theta. Okay? Question 14, again, just set up some values. I would do 0, 90, 180, 270, 360. But girls, this one actually will have sharp curves, I think. This one does have sharp curves. Because, what's sine of 0? If we look at a sine curve, what do you get? That's the normal sine curve down the bottom. Isn't sine of 0, 0? What's sine of 90? Sine of 180. Sine of 270 is actually -1, but you've got to square it. So remember, these have all been squared. So what do you get? 1. And sine of 360 is 0. So when you sketch this one, girls, I think it actually, you know what happens? See this curve here? Yeah, but it bounces back up. And I don't think, you know how that comes straight down there? Well, you've got to bounce it back up here.
So then
There's a sharp thing. It's actually going to look like this. It's going to look like that. If you sketch this, you're going to get this. You know why? Because this is sharp when it comes down, and instead of going down here, it jumps back up. And I think you're going to have a sharp turn, a sharp corner there. Yeah, I think you cannot differentiate at x equals 180. See, you know how normally the curve is smooth and it goes down? Well, here it's bouncing back up because you're squaring. And I'm pretty sure this point here, when it bounces back up, it's going to be a sharp point. Okay? So this is differentiable for all theta, or whatever that symbol that is. Who's Greek? That one. What's this one? Differentiable for all that symbol. What's it called? Except C equals 180. And multiples of 180 as well. I think it'll happen at 360. Do you know what I mean? I don't even know. I haven't even seen the question to know. But again, differentiable for all C except for 180, 360, etc. Any multiple of 180.